All right, in the first half of our lecture today, we looked at how we can build a binary heap and how that lets us implement a priority queue interface. For the second half of our lecture today, and because of the storm, we have to do this on YouTube. But the nice part about doing it on YouTube is I can take all the time I need to show you a bunch of really cool tricks on how to debug a buggy program. So we are starting off with our Fibonacci function. We've shown this to you in the past 2 lectures, but in case you're coming at it fresh, we have 4 different ways of implementing Fibonacci, starting with a simple recursive version where fib of n is fib of n minus 1 plus fib of n minus 2. We have a tail recursive version. We have an explicit looping version. And finally, we have a version that uses Vaver's streams or lazy lists. But before we get to those, let's start off with the simple recursive Fibonacci implementation. Here, if n is less than or equal to 1, we return 1. Otherwise, we return this set of recursive calls. And before we do anything, we have some tests. What do our tests do? Well, the tests are the same for all 4 versions. Each test runs this helper function, and it asserts that when we run the function with 0, 1, 2, 3, 4, etc., we get out 1, 1, 2, 3, 5, 8, 13, and so forth. That's our Fibonacci sequence. That's what we're expecting. And before we start introducing bugs, we're just going to make sure, for the purposes of this lecture, that everything is working. All of our tests are passing. So far, so good. Let's introduce a bug. Let's say that when we were coding the simple traditional recursive Fibonacci function, instead of saying n less than or equal to 1, we did this, n less than 1. So it's a bug. How might we discover and fix that bug? Well, as always, we're going to run our test. And what our test is going to say, after it compiles, oh, it's not working. Step 1, always look at the output from the test. In this case, it says we expected 1 and we got 2. Well, we don't need to see the difference. We know the difference between 1 and 2. Those are different numbers. And this is what's called a stack trace. It shows us where our code was when it failed. These are hyperlinks. So we know that we failed at Fibonacci test line 43. Fibonacci test line 43 means that we passed line 42. So we got the correct answer for fib of 0, it returned 1. But for fib of 1, it did not return 1, it returned 2. So now we know what failed. Let's see how we might diagnose this. I mean, since I introduced the error, you know what the error is, but let's pretend you didn't know what the error was. How might you figure it out? Well, this is the standard thing that every programmer loves to do, is to set breakpoints. So let's use IntelliJ's breakpoint facility. I can take my mouse and move it into this column next to the code, and I can click, and I can say, click, see the red dot? The red dot means I've set a breakpoint at that line. So if we're running in the debugger and code hits this line, then the program will pause and let us look at it. And rather than using the normal run button up here, instead we're going to use the button right next to it, which has a picture of a little bug. You can see it's sort of like a little ladybug. We click on it, and what will happen is the program starts running, and then it pauses when it hits the breakpoint. Now at this breakpoint, IntelliJ is telling us several things. It says, I've got one variable defined here, and that variable's name is n, and its value is 0. So that tells us what we're about to be working with. In this column, you can see that we started from fib classic test line 23, which we can click on, and that called test any fib, which we can click on, and we're now in fibfunc.apply, and we can click there. And so we can look up and down the call stack. And at each level of the stack, if there are local variables, we get to see them. So this is how we can look at our program and see what's running. This blob over here lets us see what thread we're on. Right now, we're not doing fancy multi-threaded programming in Java. As long as main is selected, and you can see here it is, you're looking at the right stuff. And lastly, this funny looking funnel thing, this lets us toggle what we're looking at. All this yellow stuff, this is JUnit running our unit tests. And there's a lot of stuff here, and we really, really don't care about any of it. So we click this button, and all of the code that's not our code disappears. And instead, we're only looking at our own code and finding bugs in our own code. Well, we set a breakpoint. What can we do once we're at the breakpoint? Well, we're interested in the case when n equals 1, because we already know we got the right answer for n equals 0. So we hit the breakpoint, but not when we wanted to hit the breakpoint. So the simplest thing we can do is these buttons along the left. The red square says stop running. This one on the top says rerun from scratch. That's not interesting. This one says rerun the failed tests. Well, we're already running the failed test. That's not interesting. This one that says resume program. So it says, okay, we're paused right now. Keep running until we hit the breakpoint or any breakpoint again. Let's try that one. Click. This time we're running with n equals 1. At that point, we now know this is the input where the bug happened. And now, well, we can either try to read the code and intuit it, or if we're not sure what's going on, we can single step the program. This is where these buttons on top come in. This one is what you're mostly going to be using, step over versus step into. The difference is when there's a function call, step over doesn't, it basically sets the next pause point to be after the function returns. So if there's a function that's doing something like printing output or whatever, I don't need to see the guts of the function. I just want to step over it and keep going in my own function. This thing over here turns out to be really interesting, run to cursor. So I know that n is not less than 1. I know the next thing is down here. I can simply hit run to cursor, boom, and then it jumps to where I knew it was going to jump. But if there was a bunch of junk in the middle that I didn't care about, I can say go to where I care about. At this point, well, now what? The program is really very simple here, so there's not a whole lot of challenge, but what I should observe is n is 1, and I'm calling fib of 0 plus fib of -1. And knowing that fib of -1 shouldn't be a thing, and the only reason this is working at all is because I've just defined that for all negative numbers, we're just going to return 1. But I should hopefully recognize that I'm overdoing it. At any rate, we're going to do something, but let's pretend I still didn't get it. Let's do something a little bit more interesting. Watch this. Let's use our logging library. So I can say log.i, and okay, I need to import the logging library. So on my Mac, I'm going to hit Option Enter. On your PC, it's a different key sequence, but Option Enter. Now I've got this log method takes 2 arguments, both strings. So for the first one, I'm just going to say fib, and for the second one, I'm going to say what I'm working on. And I could say, fib of n. Now, when I run the program normally, I'm going to kill the debugger and just hit run. And what I'm going to see is a whole bunch of logging text, and then eventually, so this is logging text generated by the logger, this is logging text generated by the fib function. And it says fib of 0, fib of 1, 0. So I can see the order. These are just fancy print statements, but they're useful fancy print statements. And what I should hopefully observe is, wow, where did -1 come from? I wasn't expecting that. And then I might realize, oh, okay. At that point, I might comment this out, or I might go into the logging library and say, just disable that. But for now, I'm going to first and always make sure that my unit tests pass. And if they do, then I'll be able to move on to the second example where the debugging is going to get a little bit more interesting. All right. We're going to comment that out, and we're going to move on. So next, we're going to do our tail recursive Fibonacci. In this version, remember, the external interface for the function is that we take an integer n, and then we call our helper with 4 different numbers. So a start, an end, and then these 2 values, p1 and p2, that we're going to be using. They start at 1, 1, and then the p2 moves down to the next p1, and for the next p2, we add them together. And just to remind you, the code as is works just fine. And we know because it passes the same tests. So let's introduce a bug. This is a complicated function, easy to get wrong. Let's say I replace p2 with p1. A simple error, anybody could make this mistake. If I run the program, what happens? Oh, the tests fail. I expected a 2 and I got a 1. How did that happen? Well, first things first, we're going to read the error output. And it says that it failed at Fibonacci test line 44. So that means we got the correct answer for the first 2 assertions. And it's the third assertion that failed. That's kind of interesting. And yeah, we were in the middle of testing fibtail recursive. So let's go so we know that n equals 0, n equals 1, we got the right answer. But n equals 2 was when it didn't work. Interesting. Well, where do we set the breakpoint? Where do we want to start looking? Maybe we should start looking here. Now the problem is we are going to hit this place, and initially we can see the values of p1, p2 start and end. We can even go up 1 and say that we're dealing with n equals 0. We don't care about n equals 0. We want to get to n equals 2. So let me show you a trick, a really awesome trick. So we know that n equals 2 maps to end, so we really want end to be equal to 2. Watch this. I'm going to right-click on the red dot. And what comes up is this. It says I can enable or disable the breakpoint. Forget the all versus thread, but this condition part is really interesting. So I can say only break when end is, say, greater than or equal to 2. You can write any Java expression that evaluates to true or false here. So I'm going to stop and rerun things. And what we're going to find is, end is 2. So we were able to jump over the stuff we didn't care about by setting a condition for the part that we do care about. And in fact, we can roll up here, indeed n is 2, and we can roll over here. We've already passed the first 2 assertions, and we're working on the third assertion, which we already know fails. Okay, how do we find the bug? Well, just because we're able to start at the right place doesn't mean the bug is obvious. You know, I cleverly typoed what should have been a P2 with a P1 plus a P2. So I could be, let's step. At this point, P1 is 1, P2 is 1. I want to see what happens in the recursive call. So if I hit step over, the recursion's already done. That's not what we're interested in. We want to go deeper. So we're going to step into it, and now we went back up to the top. Notice how we have fibtail recursive helper. There are 2 of them up here. The first one, P1 is 1, P2 is 1. The next one, P1 is 1, P2 is 2. And start is less than end, yes. So we can keep stepping. We're going to call it again. P1 is 1, P2 is 3. Start equals end. Now it's going to return. So just by looking at the variables, we can observe that P1 never changed. P1 was supposed to change. And so simply by looking at each of the stack frames, I can see that P1 is not changing at all. And that should be our hint that we're doing something wrong. And then we should hopefully have the insight that, yeah, right, this should indeed be a P2. Another way that we might have discovered this is, again, to add logging. So what might be our tag this time? It would be nice if our tag was something different than the last one. So we might call it fib_t for tail recursion, and we might say, you know, running with P1 plus, and then a comma, and then P2. Too much work. There's a version of this function that's slightly more useful called iFormat. And in this case, we can do running with P1 equals a number, P2 equals a number, start equals a number, end equals a number, P1, P2, start, end. So we can go look at this function if you'd like. I'm hitting Command B on my Mac. And this is our log code. And what iFormat does is it takes a tag string just like regular. It takes a format string just like system.out.printf and just like string.format, and then a set of things that fit in. So this will give us nicely formatted results for all the arguments when we run it. So let's run it, and what do we get? So we can see that the logging system did its own stuff, and now here we are in the fib_tail recursive version, and it's printing all the steps out for us. So when should I use the single-step debugger and when should I use the logger? Well, it's really up to you. I generally prefer logging. Logging is usually easier to add, it's easier to take away later, and it doesn't require learning how to drive a particular debugger and how do I set a conditional breakpoint. It's a lot easier just to do logging. But anyway, from looking at this, we should observe that P1 is not changing. That should give us a hint that where our bug is. And then hopefully we will have the insight that this is meant to be P2. And if we run the same test again, leave the logging in for now. And you can see that now we can see all the different tests running. And we can see that we started with P1. In this case, we're trying to get fib of 6. So we start off with 1, 1, then 1, 2, 2, 3, 3, 5, 5, 8, 8, 13. So the Fibonacci sequence progression is now working the way it's supposed to work. And we can see that just from looking at the log, which is much less painful than having to deal with single-step debugging. All right, next up, let's look at our looping version. So this is a loop unrolled version where we took the tail recursion and turned it into an explicit while loop. Well, let's remind ourselves that this code works correctly. Oops, run, and what we'll see is it passes the test. I'm sure you're incredibly surprised. What would be a common, easy to make mistake? Let's say that rather than computing the new P2 and then storing it into the old P2, let's say that what I instead did is I said P2 equals P1 plus P2. Now the bug here is that I've overwritten P1 and now I'm using the wrong P1 to compute the next P2. So this is clearly a bug, and this is a very, very common error that many, many programmers will make. Let's see what happens when we run our tests. Well, we got a little bit further than we got in some of our prior tests. So we were expecting a 3, we got a 4. And if we go to the test, it says that we passed the first 3 asserts, and we failed on this one, where the number that we're trying to find Fibonacci number 3, and instead of getting a 3 out, we actually got a 4 out. Interesting. Very interesting. So this, when we have this looping structure that's constantly overwriting things, well, once again, we could log or we could set a breakpoint. I'm going to go for logging. And I'm going to say, instead of fib_t, this is fib_l. And I'm going to say new version, or new state. I'm just we're printing P1, P2, start, and end over here happens to be called N. And if we run it again, not even messing with the debugger this time, we just want to see what the state is each time. Now, where should I have printed this? In the middle, at the front, at the end? Well, I should either, right now I'm printing it in the middle of updating the state. So I can already tell you that it's going to be really hard to figure out what's going on here. So let's do this all the way up here. Well, no, we want it in the middle of the loop. Let's do it here. Okay, so the first thing we're going to do, and it's not even the new state, it's just the loop state. We're going to print the 4 variables. So initially, we would expect P1 to be 1, P2 to be 1, start to be 0, and N to be S. So initially, it's just going to be the initial arguments. So 1, 1, 0, 1, that's what we expect. And then this one exits very quickly. 1, 1, 0, 2, 1, 2, 1, 2. Oh God, this is still more work, right? I have to figure out where, because I'm only interested in doing any of this when N is 3, because 3 was where I had the problem. Well, how am I going to do that? Probably the simplest thing is to add some logging up here. So now I'm just going to, when I start the fib loop, I'll print the value of N. What's the difference? Watch the logging output of this. So a bunch of junk we don't care about. Now I can see I called it with 0. When I called it with 0, the loop never ran. When I called it with 1, the loop ran once. When I called it with 2, the loop ran twice. When I called it with 3, the loop ran 3 times. So already I'm getting some really useful information in my log. And by having a separate log entry that says that we're starting the loop versus one inside the loop, I have much better visibility into what the loop is doing. So this was the case where it blew up, and I can look at the progression. 1, 1, 2, 1, 2, 4? Isn't this supposed to be 1 plus 2? Shouldn't that be 3? Why is it 4? Oh, I see what I screwed up. And so now I can replace, because I had to compute the new P2 using the old P1, not the overwritten P1. And once again, if I run this, we're going to see that the tests passed. And if we look at the log, we can see that when I'm calling it with n equals 6, that I can look at the progression of the P1s, I can look at the progression of the P2s. Everything I need to see is in the log, so I don't have to mess with the IntelliJ debugger at all. All right, the last thing I want to show you is the lazy list / streaming version of this. This is using Vaver's streams, which are a lazy list implementation. And when you're writing code like this, it's actually very, very subtle. It's very, very easy to think in your head what you want, and then you type something else, and it's hard to realize that the thing that you typed is wrong. Well, first let's make sure that the code that we have works. We're going to run that. Say, okay, it passes the tests. But now let's figure out what would be a common error that somebody might make. Let's say I forgot this map at the end. That would be a super easy mistake to make. Well, now we haven't even run the program yet, and already IntelliJ is telling us that this is not going to work. Well, the first thing that you should do is look at what it's saying. Red squiggles, it says, well, I was expecting an int, but what you gave me was a tuple 2. And I'm pretty sure that when you told me that you're returning an int and a tuple 2 is over here, those are not the same thing. You can't put a tuple 2 where an int is expected. That doesn't fit. And if we tried to compile it, if we tried to run it, it wouldn't run. What would happen is the Java compiler would say, whoa, those are incompatible types. Now, Java doesn't know whether the bug is that this int ought to be tuple 2 of int and int, or whether the bug is that this thing needs to somehow be an integer rather than a tuple 2. The red bulb is offering you a bad choice. So IntelliJ is offering to change the return type of the function, which is not what we want. So be super careful with these yellow bulb and red bulb suggestions. This suggestion would make things bad. Instead, I'm going to show you how we can use, it's not talking about using IntelliJ as much as it's using Java to break these expressions down step by step in order to make them fit together and debug properly. So what we're starting with is our start tuple, and that's a tuple of 1 and 1. Now, I'm pretty sure that the type of this is tuple 2 with integer, but I can verify it by holding down the Option key and mousing over. And now right now it's telling us, yeah, when I mouse over the name, it says this is a tuple 2, and the type parameters are integer and integer. So I don't have to put the type over here. I can just use var because of Java 11, but I can always make sure that I got it right. We're starting with a tuple that has 2 1s in it. And I know that our lambda that's going to evolve the state for the stream is something that is a function from a tuple 2 to another tuple 2. It's right over here. But let's pull it out. So I'm going to copy that, paste it, var mapping lambda equals. Well, this doesn't actually work. First off, there's the wrong number of parentheses, but it still doesn't work. The reason why is that it doesn't know what the types are for the lambda. So we've really got 2 choices. We can add the types in here. Now what's unhappy? I'm holding down the command key and moving over that, and what it's saying is Java is not smart enough to figure out that this is a function, actually a by function from integer and integer to another integer. So sadly, even though we might try to declare the types here, it just doesn't work. And maybe if we replace, nope, it still doesn't work. So unfortunately, when we want to bring this out, we have to, rather than var, we have to say this is a by function from integer and integer to integer. And we need to import it. And oh, now what? Oh wait, it's not a function from integer and integer. It's a function from an integer and an integer to a tuple 2 of integer and integer. So the type of this lambda is pretty intense. Normally when we write the code this way, we don't have to specify the type. But when we're trying to debug a complicated expression, it's useful to go to this exercise of saying what the types are that we expect. So now let's replace things here. We're iterating from the start tuple, and let's say that we're not really sure exactly what we're doing yet. So instead we're going to put this mapping lambda thing. That doesn't work either. Why not? Well, Oh, big, long, ugly error message. The thing that you hopefully ought to know is that, okay, iterate takes two arguments. It takes a starting value and then a function that maps from the old starting value to the next one. And in this case, our starting value is a tuple 2, and we have a function that wants two integers and then returns a tuple 2. So this function, or lambda, that we're trying to pass in expects two arguments, which are integers, but so the mapping lambda has this signature, and we need something that looks more like that. The signature of the lambda is all wrong. And then we might recognize, oh, right, we never deconstructed the tuple. So how do we deconstruct the tuple? So what we really need, so this is we need another one. In this case, we need a function from tuple 2 to tuple 2. And this function, yes, I'm going to import the function definition by hitting Option Enter. And now let's give it a name. So this is the tuple successor, say. And what it is it's the old tuple arrow, old tuple dot. Now, tuple has this map method, and that's the one that we want to use. And the map method, really, it's a map. What it does is it breaks out the two entries in the tuple, and we can actually then use our mapping lambda, and it all fits. Now, if you're not sure whether that map is the right thing or not, I'm going to hit Command B on my Mac. Oh, so we're in the middle of the Vavr code. Which Vavr code? Well, we need to go to the sources. In this case, it's in my Comp215 code directory in the libs directory, and where it says Vavr Comp215 sources, we made some modest customizations, so that's why we're including that jar file. I say okay, and now this is the real map function from Vavr. And what it does, we can say that it applies the mapper and it breaks out the _1 and _2. It breaks out the two components of the tuple. So we can see that the tuple2.map method does indeed do what we want. All right, let's get rid of this and go back here. We're getting a yellow bulb suggestion. Unchecked call to map. Because these aren't just any tuple 2s. These are tuple 2s of integer and integer. And we need to do the same thing here. Now, the yellow light bulb goes away, the code is clean. The highlighting is clean. As you're working, as you're building out these awful type signatures, don't move on until IntelliJ gives you a clean bill of health. Right? When I forgot to have the type parameters for tuple 2, when I had it like this, now this map function is confused and it's talking about raw types. So we don't like talking about raw types. We don't just mention tuple 2 by itself because we know it has type parameters. So get in the habit of getting your code clean. Now, this function from tuple 2 integer to tuple 2 integer, this is really unwieldy. And this is why Java 11 added, or really Java 10 added all these var statements. But anyway, we're just doing this as a debugging process. We'll pull it all back together at the end. Okay, so we're not using the mapping lambda. We're instead going to use this tuple successor thing. Now all fibs worked, but we're still not happy. And of course, we secretly know the reason why, because we forgot to do this part. But I can tell you that all fibs, just by holding down the command key, is a stream of tuples of integers. And I'm trying to return one integer rather than a stream of tuples of integers. So clearly I need to do something. And in this case, it's this map call. So I could now have another var So this thing is really all fib tuples. And now I can say all fibs equals all fib tuples dot underscore 1, I believe. Nope, that doesn't work. And the reason it doesn't work is that there is no underscore 1 because it isn't a tuple, it's a stream of tuples. So what are the methods on here? All of those things. I can append, I can insert, I can prepend, and I can map. And I can map, in this case, it's a tuple, and it's a tuple dot. There's the tuple methods that I need. So I want to get the underscore 1, which is the first element of the tuple. Now, did you notice how when it auto-completed that, it offered us a direct access to the field, to the member variable itself, and there's also a function. So why would I prefer the function over the direct access? Well, the cool part is when I do it with the function, and by the way, if I'm not comfortable that the function does what I want, Command B, and I can see that the code is very straightforward. It just returns the member anyway. So I'm comfortable using it either way. But when I do it this particular way, I get a yellow light bulb that says I can replace the lambda with a method reference. Oh, that's cute. Now what's the type of the all fibs? Now it's a stream of integers. And now I bet you my code works. So we're going to run the test. And the test passes. Once you've got code in this really verbose, terrible fashion, it's actually, this code is great because now you know that it works, do a commit so that way you don't lose it, and now we're going to start putting it all together again. So all fib tuples we can replace with stream iterate of this other stuff. And all fib tuples, see when I mouse it, when my cursor is on it, it highlights. It's defined here, it's used here, and that's it. Which means I can substitute. I can delete, copy, paste, and hey, I'm not sure if I broke anything or not. Run the tests again. The tests pass. So now I can keep repeating this process. So that start tuple, where is it mentioned and where is it used? Only those two places. So once again, I'm going to cut and paste all of this. And in here is tuple of 1 and 1. Test to make sure I didn't break anything. All right, now let's get rid of these horrible, awful, long things, and let's put it all together. So this mapping lambda, let's put that in here. So I'm going to cut and paste. Let's make sure it works. It works. And the last thing we're going to do is take our successor function, which is defined there, and use 3 lines down and nowhere else. So now we can take that whole string, place it here, delete that, get rid of this thing. Wow, now we've got a super long line. Does it work? Let's find out. Yes, it does. In fact, we can even go one step farther. We define all fibs here, and we only use it in one place. So in fact, we can say return all of that, get n. And now we've got this super long, crazy thing, and we can see, hopefully, that it works. So now, what do we do with a horrible, awful, long expression like that? The first thing you should always do is format it properly, because this is just unreadable mess. So we're running the Google Java formatter, and you can do it. So now it made the code a lot more legible, and we can see that there's some steps happening. We're forming this stream of tuples, then we're mapping, then we're getting. So the indenter, it's the same exact program, but it just made it more legible to us. All right, one last trick I want to show you for the day. Now, if we look in our log library, we've shown you log.i and log.i format. There's one other useful thing in here, which is down at the bottom, and it's this IWrap thing. So this is a higher order function, and what it does is it prints all the, it takes, you give it a lambda, and then it returns another lambda. And that second lambda logs the input and output to the first lambda, and then runs the first lambda. So this func.apply, it runs the first lambda, saves its output, logs the input and the output, that's what this part does, and then it returns the output. Let me show you how this works, because it's really cool. So deep in the middle of this thing, how can I track what's going in and out of that lambda? Right? I could set a breakpoint. I clicked next to that number 71, and IntelliJ is saying, I've got 4 different places. I could just set a break at the beginning of the line. I could set a break inside this lambda where you are, or I could break on, there's 2 different lambdas going on, or I could break all of them. Tell me where you want the breakpoint. This way lies madness. Instead, let's wrap this lambda with another lambda. So if I say log.IWrap, and in this case, it's fibstream. So this log IWrap thing takes in a lambda and returns a lambda. Now, just to make my code more legible, I'm going to let the auto formatter make it pretty. Didn't really change much, except it put this on its own line. And now this internal lambda is now being logged automatically. What's going to happen here? Watch this. Oops, I didn't want to run the formatter again. I wanted to run the stream tester. So now I have all of this code that says the tuple 1,1 got mapped to 1,2, 1,2 got mapped to 2,3, 3,5 got mapped to 5,8. So we can see what every single one of those calls is doing. But we don't see anything about when. So let's add one more log call. So we're just going to print the number being logged when, I'm going to print the argument, and we're going to see something funny happening. So actually, we're not seeing anything super crazy. We're seeing that we're starting fib stream of 5, and then the computation happens. But watch this. So I'm going to save the result, but I'm going to do an extra bit of logging here. So, not super exciting, but it's interesting to be able to say that I'm starting with a 5, then I do a bunch of work, then I get out an 8. I'm going to do one more trick, though, to really show off the laziness working. Right now, this this stream, we're recomputing the stream every time. And maybe that's a thing that we don't want to do. Maybe we want to only compute the stream once because we know it's not changing. So in order to have a local variable, I need to change this from an interface to a class. No big deal. And now I'm going to be able to take this whole expression out here, and I'm going to say, well, what is it? It's a stream of integer, and we're going to make it private because it's not something we want anybody outside to see. And this is our fib number stream equals that thing. So now I have this stream of the Fibonacci numbers that's infinitely long, but it's lazy, so it's no big deal. It hasn't been evaluated. And this whole result part is fib number, get the nth thing from the fib number stream. I'm sorry, this has to be static for that to work. Now it's happy. So what's going on now is we're creating this infinitely long stream. We're only ever then getting from it. So now what we're going to see is when the laziness happens. Here's the fun part. So I'm going to say run. Ooh, inconsistent constant pool. That's really interesting. That probably shouldn't have, I think what happened is some kind of compiler error. So we're going to do a rebuild project. Changing from interface to class, I think might have caused a little bit of confusion. We're going to see if this fixed the problem. Yep, sure enough. Java is weird sometimes about incremental compilation. So here's what's happening. Let me make this a little bit bigger so you can see it. So we ask for a fib stream of 0. It just returns 1 right away. We ask for fib stream of 1, and it has to iterate. So the lambda ran. We ask for fib stream of 1. It can, so that's the return, that's the input, that's the computation, that's the output. That's the input, that's the computation, that's the output. So the thing that you should observe that the logging lets us see loud and clear, but would be almost impossible to figure out with the debugger, is that we can see when the lambdas run by having the lambdas have a side effect of dumping out to the log, and the log lets us observe that the stream is lazy and only computing once. So it's giving us this memoization behavior as well. We're going to spend a lot more time talking about memoization next week in class, but what I'm hoping that you have taken away from this is that as your programs have expressions that get larger and more complicated, what you should always be thinking about is not how do I step through it with a debugger. The question is, how do I break large expressions down into smaller expressions, and how do I make those smaller expressions, how do I just define each of them in series and make sure that the types connect, that the output of, that the argument that something is expecting matches up with what I've got. If all the types match up, then there's a much better chance of your program running the way you were expecting. And when in doubt, add lots of logging after that. All right, that's it for our debugging demo. I hope everybody's doing well after the storm, and I'll see you all in class on Monday. Thank you very much.